Hello, welcome to this first video for our Calculus 1 course. In this video, I'm going to introduce us to some of the major ideas that we're going to explore in the first theme of our course about the limits of functions. And so I just want to whet our appetite a little bit for that theme of topics, maybe jog our memories about some concepts about functions and graphs that we've studied before this course, and just try to get us thinking about mathematics again. So here's a specific example that I want to look at that's going to motivate the concept of a tangent line, something that's going to be really useful for us and we're going to spend a lot of time investigating. Consider the function f of x is negative 16x squared plus 48x, and you can see the graph of that function down here. That's that red curve. My main question that we're going to explore in this example is what's the slope of the curve there at that point where x is 3, right down there. What is the curve doing there? How curvy is it? How slanted, how tilted, how steep is the graph? Well, the question of the slope of something, that question we can answer when I'm talking about a line. I know how to find the slope of a line through 2 points. You can see there I've written the concept for the slope of a line. If I have the coordinates of 2 points and I want to find the slope of the line that passes through those 2 points, I just need to find how vertically separated they are, the rise, and how horizontally separated they are, the run, and the slope is defined to be the ratio of those two, the rise divided by the run. Now that works for a line because if I pick any two points on a line, the slope between them is what the slope of the line is. It never changes. It doesn't matter what 2 points I pick. But on a curve, like this parabola in the graph you see here, the slope seems to be different at different places. If I pick 2 points on the graph like over here, well, the line between them is going to be pretty steep. And if I pick 2 points like over here, the line between them is going to be pretty shallow and have a negative slope. So the curvature is changing. The slope of the curve is different at different places. And we don't yet know what it means to find the slope of a curve as opposed to a straight line, a curve at a specific point. And that's really what I'm asking in this question. But this is also such a deep idea that we're going to spend quite a bit of time in our course exploring what that means, how to do that, and how to use it. But I just wanted to introduce you to some of the big ideas with this example, so don't feel like we're going to cover all of these questions in full detail in just this one introductory video. So we don't yet know what it means to find the slope of a curve at a specific point, but that's kind of what I'm going to outline in this example, in this video. And then one benefit of finding that slope is that we can find the equation of that line that you see in the graph here, that we're going to call a tangent line. Tangent meaning that it just glances off the curve. And that concept of tangent line is going to be used by us in this course a lot. So for now, just as a starting definition, we can say that this line over here in the graph appears to be tangent, to be lying tangential to the curve, because it just kind of kisses off the curve. It just glances off the edge of it and only intersects it at that one point at x equals 3. Now that's a pretty vague definition so far, and as mathematicians we like to get a more specific definition that doesn't have any vague or fuzzy notions to it, like glances off, that you can see I've written in scare quotes there. But just to start now, this is fine. We'll dive into this concept and be more specific and formal about what I mean later. Alright, so let's explore what I mean by answering a few follow-up questions. There's that same function, and now I'm going to assign a meaning to it. I'm going to tell you that it represents something. Let's say that this function represents the height of a ball that was thrown upwards from the ground at a certain speed. And so I'm thinking of this function's input, the x value, as the time, the number of seconds that have passed since the ball was thrown. And the output from the function, f of x, the output, is the height of the ball in meters at that specific x moment in time. And so maybe just looking back really quickly, you can see the shape of the graph here, and you might know from just experiences being a human being or from having seen it in other courses before that the trajectory of a thrown ball, if you ignore air drag and wind forces and things like that, will have the shape of a parabola like this. So it's not all that crazy that I'm saying this quadratic function represents this physical scenario. So I want to use this function to find the average speed of the ball over a specific time interval. So the key idea to use here is that speed is distance divided by time. It's a rate of motion. So to find your speed, you ask how far did you travel and how long did it take. If I told you I went 100 miles and it took me 4 hours, you know that it took me 25 miles per hour on average, 100 divided by 4. So that's the same principle I'm applying here. The average speed of the ball is going to be the distance it traveled, the change in its height, and that's what I'm doing here when I calculate f of 3 minus f of 1.5. That's how far the ball traveled up or down over that time frame from 1.5 seconds to 3 seconds. And I'm going to divide all that by the change in time, or how many seconds have elapsed, and that's what 3 minus 1.5 accomplishes. And I've noted these in blue and red, and parenthetically as rise and run, to remind you that really what I'm doing here when I find the average speed like this, and I do the change in the output of the function divided by the change in the input of the function, this is exactly the same concept as slope, or rise over run, that we were talking about a few minutes ago. And so in this case, if you plug in 3 and 1.5, you get 0 and 36 as the outputs of the function respectively. And so if I do that calculation, I get negative 24, and the units on that are meters per second, meters divided by seconds. The output of the function's in meters, the input is in seconds. So this is telling me that over that time frame from 1.5 seconds after releasing the ball to 3 seconds after releasing the ball averaged 24 meters per second downwards. It was traveling down towards the ground. That's what the negative sign means. It's downward motion. Let's ask and answer the same question about a different time frame, something that's a little bit narrower around the x equals 3 point that the original question was about back on the first slide. Let's repeat the same question, but from 2 seconds to 3 seconds. And then we'll do it again from 2.5 seconds to 3 seconds. And so I'll save you the trouble of writing out and showing you what I'm doing on my calculator, and just say that you can pause the video at any point and replicate these steps for yourself on your own to make sure that you get these same values. But I find that from 2 seconds to 3 seconds, the ball averaged 32 meters per second downwards. And from 2.5 to 3 seconds, and there's my calculations right there, the ball averaged 40 meters per second, again, heading downwards because of that negative velocity, negative speed. And so we might wonder, well, what would keep happening if I made x get closer and closer to x equals 3? So if I did from 2.9 to 3 seconds, if I were somehow to be able to zoom in on that 1/10 of a second of time, what would the average speed of the ball be? Or if I could zoom in on 1/100th of a second, what would the average speed of the ball be? And as it turns out, if I keep doing that, those average speeds don't change greatly. They seem to get closer and closer to a specific number. And so if you do those calculations and follow very similar formulas to what we were doing up there a second ago, you get these results. From 2.9 to 3 seconds, over that 1/10 of a second moment in time, the ball averaged 46 and a little bit more meters per second heading downwards. Over the 100th of a second, just before x equals 3, it averaged 47.84 meters per second going downwards. And over the 1,000th of a second, it averaged 47.984 meters per second heading down. And if you keep adding more 9s to that 2, you keep adding more 9s to that decimal expansion down there, and so it turns out this is getting really, really close to negative 48 meters per second. And I know this may seem a little, I don't know, silly maybe, to guess and check at numbers like this, but this is the process that we have right now. And a little bit later in the course, we're going to formalize this process and say what it is that we're really doing and come up with some general formulas to help. But at least in this specific situation, I hope that you can also see how what we're really doing by finding these average speeds over smaller and smaller intervals of time, we're really getting closer and closer to answering the question, how fast is the ball going right at that moment at x equals 3 seconds? If I had a radar gun pointed at the ball right as it hit the ground there at x equals 3, how fast would it be going? What would my radar gun read? And as it turns out, it would say exactly 48 meters per second. It wouldn't tell me it was negative because it was going down. I would have to figure that out for myself, but it would tell me the 48. And so here's what we really did there. We were just finding slopes of secant lines. If I chose some value x equals a, and so we were just using a equals 2, and then 2.5, then 2.9. If I go from x equals a to x equals 3, the line through those 2 points on the graph is a secant line that cuts through the graph. Let me jump back to the first slide with the graph on it and say that if I picked a point over here, like x equals 2, and then the point x equals 3, and I drew a line through them, that's the secant line that I'm talking about. We found the slope of that line a few minutes ago, and then we found the slope of the line through 2.5 to 3. And then we made it from 2.9 to 3, and we kept picking the second point to be closer and closer to 3. And by finding the slopes of those lines, we were doing the rise over run concept. And as we let that point A approach 3, those slopes seem to approach a specific number. That's the slope of the tangent line at that point, negative 48. And so if you look at this graph here, indeed, the slope of that line right there that I have graphed for us is negative 48. And so in terms of what that function represents, what we just found is the instantaneous rate of change. By looking at a bunch of average rates of change and seeing what happened as the 2 points got closer together, we were really doing a limit. That's the major theme that we're investigating now, limits of functions. And so in the limit, finding that the numbers were approaching negative 48, that's the instantaneous rate of change of the function. That's the velocity of the ball right at that moment. And so a lot of the time we'll use slopes of secant lines like that to talk about average rates of change of something. It's not always necessarily going to be, height and speed or velocity, things like that. But we will be using functions to represent certain quantities in the real world. But also, this being a mathematics course, we'll sometimes just ask and answer some interesting mathematical questions, just because we can. So, for example, in the process of this video, we talked about a tangent line and what that could mean. So here are a few examples of graphs, and I want you to, in a second, pause the video and look at each of them, and think carefully and jot down some notes and maybe some questions, and then unpause and listen to what I discuss here. But I want you to think about, for each of these graphs, at the point where x equals 0, like for example, this point here, and this one, and this one, what is the tangent line at that point on the graph? What does that mean? What would it look like? And if you can, estimate what you think the slope is. So like I said, pause the video and think about this for a little while, and then come back. Okay, are you ready to discuss? Here's what I found. The cosine function at x equals 0 has a tangent line that's perfectly horizontal with a 0 slope. And so that graph having what we're going to call a local maximum there, sort of a peak, I can see there that the tangent line that makes sense, that just glances off the curve there, has to be perfectly flat, has to be horizontal, has to have a 0 slope. Now, you might think that the same thing would apply for the second example. It also looks like it has not a local maximum, but a local minimum there. So maybe the same idea would apply, and I could say that I have a horizontal flat tangent line. However, if I drew something like this, I think you'd have to agree that that also just glances off the edge of the curve and only touches at that one place. So what's wrong with that one? Or for that matter, what's wrong with having a tangent line that looks like that? Or a really steep one that looks like that? Or a downward steep one that looks like that? Seems like there's a whole plethora of possible slopes for tangent lines that could apply here. And so, as it turns out, we're going to have to conclude that for this example, a tangent line just doesn't make sense. There's not one possibility, there's a whole bunch, and who are we to pick from amongst all of those options? So in the future, we're going to declare that this example just doesn't have a tangent line at x equals 0. And so hopefully these two examples so far have also showed you why the concept of just glancing off the curve isn't a great definition of what a tangent line is. Because, for example, in the cosine one, it didn't just glance off the curve at that one point, it happened to glance off it at a whole bunch of other points over here, and so on. And if I continue the wave left and right, it would glance off it infinitely many times. But also, for the second example, there's too many possible lines that just glance off the curve there, so maybe that's too vague of a notion. In this third final example here, we'll have the techniques a little bit later in this course to find the slope of this tangent line that I'm drawing here. As it turns out, that one has a slope of -1. Like I said, this is not something that I'm expecting you to just see from the graph. Maybe you just kind of guess that it looks about that much. And I'm telling you right now that yes, it's exactly -1, and pretty soon in our course we'll know exactly how to find that. But you could do the same process we were doing in the earlier example by putting x equals 0 as your base point and choosing an a value very close to 0 and letting it get smaller and smaller and seeing what the slopes of those secant lines do. But also I wanted to show you this example because this tangent line, you can see that the curve is above it over here, but the curve is below the tangent line on the other side. And that's a little different from all these other examples. Like over here on the cosine curve, it was always below the tangent line. Or looking way back to the beginning, here the tangent line, the curve, is always underneath it. So I just didn't want you to get the mistaken impression that that's always going to happen that way, because here's an example where the curve goes both below and above on either side. So that's all for now. This is hopefully just an introduction to some of the big ideas we're going to dive into in more detail as the course goes on. And really in the next video, I'm going to go back and show you how to use the tool Desmos to get this kind of graph, but also to do a lot of these calculations for you. That will hopefully make your lives a lot easier going forward. All right, see you there.